Good morning, champs. Today we solve a beam carrying a distributed load that looks much more complicated than the ones we have seen before. At first glance, many students think they need a new formula, but the trick is to recognize that this load can be split into two simple triangular loads. Once we do that, everything becomes familiar. Consider a beam with a pin support at A and a roller support at B. The beam has a short overhang to the left of support A. The distributed load reaches its maximum value of 6 kilonewtons per meter directly above support A and decreases linearly to zero at both ends of the beam. Our first step is to split the load into two separate triangles. The left triangle acts over a length of 0.5 meters, while the right triangle acts over a length of 1 meter. We begin with the left triangle. The equivalent force equals the area of the triangle. Therefore, the force is 1/2 times 6 times 0.5, which gives 1.5 kilonewtons. The equivalent force acts 1/3 of the base length from the larger side of the triangle. Since the larger side is located at support A, the force acts 0.167 meters to the left of A. Next, we calculate the equivalent force for the right triangle. Again, the force equals the area of the triangle. 1/2 times 6 times 1 gives 3 kilonewtons. This force acts 1/3 of the base length from the larger side, which places it 0.333 meters to the right of support A. Now we replace the distributed load with these two equivalent forces and draw the free body diagram. The unknown reactions are AX, AY, and BY. We start with horizontal equilibrium. Since there are no horizontal loads, AX is equal to 0. Next, we take moments about support A. This eliminates the reactions at A from the equation. The left triangular force creates a counterclockwise moment because it acts on the left side of the support, while the right triangular force creates a clockwise moment. Solving the moment equation gives a vertical reaction at support B of 0.75 kilonewtons. Finally, we apply vertical equilibrium. The upward reactions must balance the total downward load. Solving gives a vertical reaction at support A of 3.75 kilonewtons. Our final answers are AX equals 0, AY equals 3.75 kilonewtons, and BY equals 0.75 kilonewtons. The most important lesson is not the numbers. The important lesson is the strategy. Whenever you see a complicated distributed load, ask yourself whether it can be divided into simple shapes. Once you replace each shape by its equivalent force, the rest of the problem becomes a standard statics exercise.